Radioactive decay law. See, when you have a sample of radioactive material, a heavy nucleus, it will start emitting alpha, beta, gamma rays spontaneously. Naturally, the initial number of nuclei will gradually decrease. At what rate they decrease, and what is the relation between the time and the number of nuclei at any instant of time, that can be obtained using radioactive disintegration law or radioactive decay law. Now, let us say that the initial number of atoms is taken as n naught, and n represents the number of nuclei at any instant of time. That is, let n be the number of radioactive nuclei at any instant of time. And let us say the rate of disintegration is represented by dN by dt, that is with respect to time how they are decreasing, the number of initial number of nuclei is decreasing. Let us say that rate is represented by dN by dt, be the rate of decay of the nuclei. Now, it is observed that this rate of decay is always directly proportional to the number of nuclei that are present at any instant of time. It implies that we can write an expression something like this: dN by dt is proportional to n, that is the number of nuclei at any instant of time. Now, suppose if you replace this one proportionality sign with equality sign, then we will get a constant lambda, that will become lambda n. We also use a minus sign there. In this case, lambda stands for decay constant or disintegration constant. The negative sign is taken because as time passes on, the number of initial nuclei will gradually decrease, that is represented by the negative sign. Proceeding further, dN by dt is equal to minus lambda n, where lambda stands for decay constant. Now, we can write this expression as dN by n is equal to minus lambda dt. Next, we can integrate on both sides of the equation, that will give you integration of dN by n is equal to minus lambda integration of dt. Lambda is a constant, therefore, it is taken out of integration, and the limits are taken as initial number of nuclei is taken as n naught, and at any instant of time the number of nuclei is n. So, limits will be n naught to n. Here the initial observation time is taken as 0, and the instant of time at any instant is taken as t. So, the limits for dt becomes 0 to t. On integrating, we will get the expression log base E n, and limits n naught and n is equal to minus lambda integration of dt is t, limits are 0 to t. Proceeding further, this is nothing but log n and on this side you will get minus lambda t after substituting the limits t minus 0, and here you can write this as log e n by n naught is equal to minus lambda t. That implies n by n naught will be equal to e power minus lambda t, and n is equal to n naught e power minus lambda t. That is the required expression for us. The number of nuclei, radioactive nuclei at any instant of time can be obtained using this expression. Here N naught stands for initial number of nuclei. From the equation we can understand that the number of nuclei will be gradually decreasing, exponentially decreasing with respect to time. The exponential decrease in the number of nuclei that takes place during radioactive decay.